Hello! In today's video, I'm going to share an experiment I'm wanting to conduct. This is a little premature. I was going to wait to make this video, but one of the guys in my advanced engine group for Cadillac engines on Facebook figured out what I have seen and what I want to test. Now, when we were talking about volumetric efficiency and when we've been talking about the inertial ram effect, he realized that if we could bump up the volumetric efficiency down here, we would be way better on the Cadillac motor. And I had the same thought. And some of this has been verified by the new formula that I have used, made up for CFM demand. And I have tested that over a bunch of motors now, and it is way more accurate than the previous one, which has gotten me a little excited about really being able to see how things work. So let me describe to you what I'm working on. Now, the primary engine that we do at Cadco, of course, is the Cadillac 500, and built lots of them, and Courtney has tested lots of them. And most of the time, a regular 8-to-1, like a 1975, 76 Cadillac 500 is like 302 horsepower at 3,600 RPM. And so that equates out to, if we take horsepower, CFM per horsepower, number of cylinders, we figure out we're using about 144 CFM per cylinder in generating that 302 horsepower. And so at a Z of 0.8, remember Z is inertial ram, and kind of shows volumetric efficiency. They're not quite hand in hand. But at a Z of 0.8, that comes out to about 180 CFM that the stock intake, stock head, stock valve can flow. And there are certain problems with the stock intake, and certainly an unported head, and it only has a 2-inch valve. And so that's part of the reason that it only generates 300 horsepower. But it occurred to me, as it did to this other gentleman, that we have airspeed in spades. We are a big motor, 500 cubic inches, with a restricted intake flow. I mean, it's only showing that it's capable of using 180 CFM of flow. Now, part of that is partly because of the intake, because I have tested the heads, and they test a little higher than that. They test at about 220. But they also have a pretty narrow pinch point, so we may be losing some there. And the plenum area on a stock intake, which is seriously divided, is not great. Now, I know what you're going to say. Well, just put a better intake on it. Well, for some engines, that's fine. And the Edelbrock intake gains us some power. But on the Eldorado, which is why the engine was built in the first place, it doesn't have a lot of hood clearance because it's front-wheel drive and the transmission is underneath the engine. That pushes everything up. In order to get it to fit, they actually took the runners and brought them down to lower the carburetor in order to get it to fit under the hood. And so those are a problem. You can't just throw an Edelbrock on it and have it fit under the hood. So one of my thoughts was, what can we do to gain some power without changing any of that? So if we take a stock engine and we do one change, what do we want to change? Well, typically I don't always look at camshaft, because I will tell you, airflow trumps camshaft. No matter how big you make the camshaft, you are better off gaining more airflow, moving the RPM up in order to generate more horsepower. That is generally the way you really should be working. But we can't do that. We are stuck with an intake, we are stuck with a head. What can we do? So when we're looking at camshaft, one of the things is, well, why don't we increase the Z of the camshaft? Why don't we increase that closing point of the camshaft? So let's look at not only a stocker cam, but what cam I have being ground at the moment that I'm waiting for, and what I'm hoping to see happen from this change in camshaft. And that's all we want to change. One part. We're changing the camshaft. So I have some parameters I've got to work in. So the stock camshaft. Now, this is a stock camshaft, but it's in an engine I call the Make It Run motor. We found a crated 75 motor that I resealed, did a couple of minor things to, and made it run. And I did that in the YouTube group for Cadillac. It's under my name and Cadillac, and it showed cleaning up the engine and making it run. Now in that engine, one of the problems, especially in 75, 76, is they added a lot of retard to the camshafts. And I talk about that in a few of the videos. And there was some retard in the chain. Of course, the chain, this was a motor that ran, so the chain was a little bit loose, and so there was some slop in the chain. And then there's some retard built into the camshaft. So even with a new chain on the cam, a tight chain with no built-in retard, I was still sitting at about 6 degrees retarded. So what I did on that motor was re-drill the camshaft gear and advance it about 10 degrees. And you're thinking, wow, 10 degrees, that's a lot. But you got to remember, it was sitting in retarded for emissions reasons. So by putting it in 10 degrees further advanced, I'm actually only sitting at about 4, it actually came out to like 4.5 degrees advanced. And so we have a camshaft. Now remember, this is a stocker cam. It's 200 degrees at 50 on the intake and 207 on the exhaust on a 115 lobe center. That's the stock cam. And like I said before, it was sitting in substantially retarded. So by putting it in at 4 degrees advanced, 4.5 degrees advanced, we wind up with an intake that's opening at 10 degrees, has a 110 degree lobe center, and closes at 30. And I expect this motor, we will test run the motor first before I change the cam. I expect it to not be a lot different than this 302. It might be up at 310, 315 or so. But you gotta remember, I have pulled back the closing point and I have increased the fill point at just past TDC. And so a lot of times this will help low end torque, but not really help peak power. And when we're talking about that 302 at 3,600 RPM, that's where peak power is happening. That's why I think I have airflow. So with that, I don't expect it to change a whole lot. I expect a little better fill up here, a little less fill down here, and this might be at 310 or something. I might see a little more torque than we normally see, but that'd just be nice. And that would verify that just doing this on the timing chain, even if you keep the stock cam, is a good idea. And that'll be our first test. Once we do that, I'm having a cam ground that we are going to test in this motor. Now, some of the parameters I have is I need to use stock rockers. They are not very strong, and so I have to limit how fast the camshaft can open. So I've picked a lobe that is not very aggressive at all. And that was done on purpose in order to try and make it hold up. Now, I am gaining some lift. A stock cam is only about 480 lift. And it's really hard to have a lobe that has a flat nose on the top. That tends to be a little hard on valve train, so I didn't want to really push that issue or have to go to a custom lobe just to keep the lift the same. And I'm thinking that the Cadillac can tolerate a little more lift without really having a problem. Now, I did put in better valve springs even when I did this, mostly because our general feeling at Cadco is that the stock valve spring isn't even enough for a stock motor. I mean, even a stock camshaft. I mean, it's like 60 pounds on the seat. And what I've gone up to is like a Z28 spring, about 105 pounds on the seat or so, and the ability to get a little more open pressure out of it. So I can tolerate more lift because I've done a spring swap. So if this cam does work out, technically it's not a one part. It's going to be a camshaft and springs. We have a stage 1 spring kit at Cadco, which is basically what I'm running in the motor. And that I recommend no matter how basic a cam you put in, because the motor just needs a little more spring. So anyway, where I'm hoping to gain power is at this closing point. Now, that goes into inertia ramp. I am increasing where the closing point happens. This calculates out an inertia ramp to a Z of 0.84. And most of the time with these itty bitty cams, you don't even get that 84% volumetric efficiency. An OE motor is going to typically be a lot closer to 80% volumetric efficiency just because the cam design is so wrong, so bad. It doesn't come close to filling. But their goal in life, if you look at this, is about low end. The stock cam, even with my advance, remember I have advanced this cam to +4 on its lobe center, but it has a closing point of the exhaust at 16.5 and an opening on the intake of 10. Now this is of course at 50 because I tend to talk at 50. So it's basically negative overlap. And that's to really help down here at idle and just off idle. And that's one of the questions that I need to answer is if I push this out, if I push out the closing point, am I going to drastically affect the idle and the just off idle power? How much will the motor tolerate in overlap and in pulse back? Because remember, as you open this sooner and sooner, when you don't have airspeed, the air wants to push back. Now I'm hoping with all of this being stock that we have the airspeed all the way down here at idle. That's what I'm really trying to figure out, is do I have enough airspeed to overcome this? Now, if the general idea works, and I'm just not quite real great down here, I can always design a cam that's just a little bit smaller than this, eliminate some of the overlap, and eliminate and move the closing point back a bit. I won't gain quite as much power, but it might be a better choice. But I kind of pushed it as far as I thought I could get away with in a couple of ways. Now, one is overlap. Now, if you look at this, I have kept basically the same lobe center. Stock is on 115 lobe center. I'm having this ground on 116. Now, the core that the cam is getting ground on is not at 116. It's at about 112. So my other problem I may have is it may reduce the base circle, and I may have to also go to a longer pusher. And that's one of the other things I wanted to see and why I pushed it. Now, we're basically not changing the lobe center, but I'm drastically changing the duration. In what I'm doing, we're going from a duration of 50 of 200 up to 246. I'm adding 46 degrees of duration to the camshaft on a stock motor. Nothing else is different. Nothing else has even been changed. This motor's never even had a valve job. The bottom end has never been apart. Like I said, there are videos on it. I lapped the valves a little bit to clean them up. I put in a little better valve spring, but for the most part, the engine is completely stock as it was in 75 when it was built. So that is a lot. And most of the time, a cam manufacturer will tell you, that's crazy. What are you doing? You're going to have no upper end power and you're going to kill the lower end power. Well, like I've been explaining in a lot of my videos, a lot of that is about airspeed. And the thing that occurred to me is the way this motor is designed, there is all kinds of airspeed. So can we capitalize that and make more power? Now we're going up to a Z of 0.98. I always try and stay below 1 because like I've said in the past, as you actually go to trying to ram a cylinder more than 100% full, you're trying to go to 105, 110, 120. You really have to have things right. And this is just a stock motor. So I don't feel I can pull that off. If for some reason this works stellar and I feel like I can get away with more, we might try another cam. I don't expect that to be the case. What do I expect to gain out of this? Well, we're basically going from what I figure is about 80% volumetric efficiency to about 100. Now remember, peak volumetric efficiency is actually here at peak torque. And so that can be a little bit different than the actual Z of the camshaft. So I'm kind of hoping that at peak torque, we are gaining right at about 100% volumetric efficiency. Now, it may cost us down here off idle, and we'll have to see. We won't know really till we run it. So that's the closing point, and that was the main thing I was looking at on the camshaft. Now, the other problem I have talked about is I've added overlap. We went from negative overlap at 50 to I now have 9 degrees of overlap at 50. Now that is not a lot. That is part of the reason I pumped up the lobe separation. And I'd be willing to try and push it further, but I'm afraid on the core we have, if I went too much further, the base circle would just get too small and I'd have trouble. And so I thought I'd start here and see how bad off it really is. Like I said, I may have to put in a plus 75 push rod in order to deal with the base circle. We'll just have to see. So at 116 lobe center, I know you guys are saying, well, you'd be better off with a tighter lobe center. I mean, you went for a tighter lobe center even on the stock cam. And the answer is yes, I did. I tried to make better use of the fill up here at 75 because I felt like I had nothing down here in the way of Z. When you look at the Z diagram, when you're down here, you know, a few degrees doesn't make a lot of difference. It's not till you start getting up in your closing point that you exponentially gain more power. And so we don't have a lot that we were going to gain by moving this around a whole lot. And Catco has run certainly some small cams that are a little bit bigger than this, you know, 212, 219, and we call those stalker cams, and they do very well. And there's dyno information available on that. So this was more about what can I do if I don't remove the stock cam just to make the engine better. And that's what I was trying to do on the Make It Run motor. I was trying to do the absolute minimum in order to make an engine that runs better. And so it'll be interesting to see how this one does too, even though I don't really expect it to be a lot more. So on this one, what am I expecting? Well, basically we should be gaining about 20% in flow, because remember, even the Z of the camshaft affects the total flow. We have, say, 180, and that may be a restriction in the intake, that may be how the intake mates to the head, because remember, the intake is down and it comes up to the head. It could be the pinch point without being ported, it could be the valve size. I mean, stock engines have a terrible valve job. Just fixing that usually helps gain some power. So I want to make use of this full 180. So by doing that, I am going to gain about, let's say, 75 horsepower. May not quite be that, but somewhere about that is what I expect to gain on just trying to get the Z up and the closing point moved out. So I'm gaining 75 horsepower from that, but I'm also going from about 480 lift or so up to about 550 lift. Now, I chose that partly because, like I said, I didn't want a specialized lobe that kept it at 480, but also because I'm hoping to gain a little bit more airflow out of this assembly. It may be the airflow is limited because of the closing point, the flow at the valve. If that's true, then I will pick up a little bit more from lift, and I may see more like 100 horsepower gain. And that's kind of what I'm hoping for with this cam. I'm really hoping to gain 100 horsepower. Go from 302 to 402 horsepower with a boost in torque. And that was my thinking. Because if you could do that with just a cam change on pretty much a stock motor, that would interest a lot of people with an Eldorado. They wouldn't really have to change a whole lot. Because one of the problems with trying to get more airflow is that stock intake is just not great. Now, if this works out pretty well, we can always try it with a different intake and see what changes. I suspect that the stock intake is part of the reason for this flow. But remember, if we boost flow, we lose inertia. If we lose that airspeed, if we lose that inertia, that could impact the bottom end. So we might be able to see kind of where the sweet spot is with a different intake of at what point does this cam that most people will tell you is really meant for higher RPM and not for making power down here, at what point does it really become a problem? And you need to realize this isn't going completely against the rules. We know in bigger motors, remember this is 500 cubic inches, they tend to swallow a lot more cam without a problem. Well, the Cadillac is even more so. Because of this restricted airflow, it tends to want even more camshaft without really generating a problem. So my question is really, how far can I push that? Can I push that up to 100% volumetric efficiency down here at peak torque and make it a better motor without really sacrificing a whole lot in the process and minimizing the number of parts that you need to make that happen? And that's really what this exercise that I'm working on is about. Let's see if we can actually make it function like I expect it to function. So that's what my plan is. I don't expect it to change the RPM a whole lot. We might see a couple hundred RPM up. And this is a real testimony to whether or not I have a good grasp on how this is all supposed to work. If I'm saying we should gain about 100 horsepower and go up maybe 200 RPM, then it happens then we know this math really does work. And that's another task that we're working on all this. So that's kind of my plan. I have this camshaft covered. It is a reverse split. It's 236 on the exhaust, 246 on the intake. And I know a lot of you are going to say, well, that ain't right. The exhaust has always got to be bigger. Well, the exhaust has got to be bigger when you're up here, when you're up in RPM, not when we're down here. And I needed to minimize overlap. I don't need to crank this out, because if you look, I am moving the opening point from 10 to 7 before. We are getting more fill down here. But on the exhaust, we're going from 43 to 52. Now, the other thing I'm not trying to do is make this way louder. The more I push this out, the louder the motor's going to be, because the pressure at blowdown is going to be higher. I also don't want to dip too far into the exhaust, because I am working way down here. Way down here. Most people on a cam this size aren't ever working that low. And so a lot of the traditional things about you need more exhaust than intake, you need a tighter lobe center, a lot of that doesn't apply to what I'm doing. I am getting more fill. I am moving this out. There is more fill happening here. And I am trying to make use of the airspeed. And we'll see if that actually works. And I know to a certain extent that goes against the grain of some people, but that's why I really wasn't bringing it up until this other gentleman said, hey, what happens if you do this? And I said the same thing. I want to know. I want to know what happens. And that'll explain also if all of this math that I've been going over actually works well. So that's my basic plan. I wish you well on your projects. I'm hoping this wasn't too long or I rambled. I just kind of did it off the cuff real quick. And I wish you all well on your projects, and you have a good day, and I will talk to you later.